We are going to go over any questions you had from that third quiz. Okay, if you have any questions from quiz 1 or 2 over the break, just come and see me individually about them, because I don't think there were any sort of general things where people had problems with. But if you had any questions from this one, if you recognize the question, you can say, hey, I did not know what was happening with question 1C, for example. I don't know, right? So anyone have any questions from number 1 that they were like, yes? Question 2, absolutely. Okay, so which of the reactions in question 1 would have a positive delta G value? What do you guys remember about delta G? What does it stand for? Gibbs free energy. And a positive delta G means something, and a negative delta G means something else.
Wait, yes, exact opposite of what I said.
This means thermodynamically unfavored. Seriously, like AP had to choose like the longest possible way of writing this, right? Non-spontaneous, thermodynamically unfavored. And negative delta G is thermodynamically favored. Therefore, I believe our reactions were non-spontaneous, non, non. And so that would make A, B, and D positive delta G. Is good? Okay, cool. Oh, why is it not moving? Anyone want 3 or 4? 4. Okay, so we have Ag, silver, in HCl. So we have an H+, we have a Cl-, and we have Ag. Those are the species that we are working with. So we are going to go to our data pages, and we are going to look up Cl, which is here. Okay, we're going to look up H+, which is here. And we're going to look up silver, which is, where's silver? It's up here somewhere. Silver, which is here. And then I'm going to back out so we can see them all. Now, if the only connections I can make from left to right are uphill, what does that mean? That means they are non-spontaneous and they won't react. So for question number 4, it will not react. And so yes, you could safely store the compound in there. Yes? I think you meant number 5, didn't you?
Oh, maybe.
It's okay. Let's take a look at number 5, shall we? Oh, whoops. There we go. Yeah. Okay. Number 5, we have HNO3. So we are going to look up, we have H, we have NO3, and we have Ag. So very similar to last time. Here we go. So we have Ag, we have H, and we have NO3. But because we have H present, we need to look and say, I have NO3 here, but I also have NO3 here. Whenever you have a choice between 2 reactions, choose whichever one has the higher potential. Yes? Okay. Not that it really matters in this case, because either of those would react with silver. Yes? Now, so I'm going to choose this one because It's a more thermodynamically favorable reaction because the hill is steeper. Yes? Does that make sense? Steeper hill, more thermodynamically favorable. That will be the reaction that happens preferentially. So now what we're going to do is we're going to take those two reactants. So we have NO3 plus 4H plus. Actually, maybe I'll do it over on the side so I have more room. Yeah, let's do it over here. There we go. NO3 minus plus 4H plus 3 electrons. That's going to go in the forward direction because this is my reactant here. And my other reactant is here. And so my products there are... Move over just a little bit. There we go. Oh. No, draw. There we go. Okay. Goes to, where did it go? NO plus 2H2O. Now my other reaction, my other half reaction, so this is the half reaction. Is this an oxidation or is this a reduction? Tell your partner, oxidation or reduction? Yes, the electrons are in the reactants, therefore we are gaining electrons, therefore it is reduction. Another way you could do it, how else could you tell if this is a reduction without looking at the electrons? You could look at the oxidation numbers. You could also look and you could say that I have a single O here, and over here I have 3 oxygens. Did it get oxidized? No, it must have gotten reduced. So if you stick oxygens onto something, usually it's getting oxidized unless the ratio is remaining the same. So an NO2, just to give you an example where it doesn't work that way. This one might look like it's been oxidized. Has it been? No, because the ratio of oxygens to nitrogens is the same, okay? But in this one, you could tell just from looking and saying, oh, I've got less oxygen, so it must have been reduced. If you stick hydrogens onto something, that also is reduction, okay? All right, and our other reaction, our other half reaction, where this is our reactant, here is the silver, and it is going that way. So we will end up with Ag plus and E minus as products. So Ag goes to Ag plus plus an electron. Okay, and now we look at that and we say, what is my overall reaction? How do you find an overall reaction when you have 2 half reactions? You multiply and add. Yes, who are we going to multiply? This one, we have to multiply it by 3. So we would end up with, do I need to do the addition or are we good? We're good? Daniel, are we good?
Yeah.
Yeah? Okay, cool. Excellent. Where did we get to? Here. Anyone want to go over any parts of 6? Yes. B? Yes. Okay, I'm not quite sure that I can remember 3 reasons. I'm like, I don't know. Okay, so I think I have 2, but I don't know what I was thinking of for the 3rd. Before Christmas, I had a 3rd. I'm like, yes. Okay, but I don't know. Number 1. I think what I was thinking for one of them was that because Fe2 plus is a reducing agent, it had to be that manganese is permanganate is an oxidizing agent. But I'm wrong in that. Why am I wrong? I have Fe2 plus. And my thinking was, I think this is what I was thinking before break. Here's Fe2 plus. And I said to myself, oh, that is a reducing agent. Yes, everything on the right-hand side of the table is a reducing agent. And if I have MnO4, that is an oxidizing agent, and you can't react an oxidizing or a reducing agent with a reducing agent, so it's a good thing that it was an oxidizing agent. But why is that argument incorrect? What is kind of special about Fe2 plus? Not Fe3 plus, but Fe2 plus. Yes? It is both an oxidizing and a reducing agent. So in theory, where is iron? In theory, we could, I don't actually know that there is anything we could titrate it with down here because everything is solid and solids don't make for good titrants. Okay, so I think maybe that is a good reason because it couldn't, there really aren't any reducing agents it could react with. So there we are. Anywho, I think that was one of them. So number 1, MnO4 minus reacts spontaneously with Fe2 plus. Yes, because we have MnO4, 2 minus. Now, it was acidified. So that means we're going to use the one with the H plus in it. Yes? Is there another permanganate? I don't know that there is. Oh yeah, there is. This would be in either basic or neutral. Okay? And if it was neutral permanganate, it would not react. Yeah? If it was basic permanganate, it would not react. But it is acidified, so instead of having H2O here, we have another reactant that allows this other half reaction to take place, and that is a favorable reaction. Is good? You're looking like, or you just, yeah, you look a little stunned, but is that just post-Christmas stunnedness? I'm feeling post-Christmas stunnedness. I'm like, I don't even know what's happening today. Anywho, that's okay. So that's one reason why. And our second reason, oh, actually, I should write here acidified. MnO4 reacts with spontaneous with Fe. And our second reason is that MnO4 minus is purple, whereas its product, Mn2 plus, is pale pink, which means when you get to the end of the reaction, all the purple color will be gone, and all that will be left is the pale pink color. So this is a self-indicator. All the purple color will disappear when the reaction is complete. Now, would you be expected to pull that out of your ear on the AP exam? I don't think so. No, that's a kind of memorization-y kind of thing but I just wanted you to be aware that that's a thing. Yes?
Is there any way of knowing that without using it?
It was in the reading. Yeah, the one that you didn't have? Yeah, that one.
I didn't Google that one.
Yeah, okay. And how about number 7? We're good? Okay, excellent. Shall we start learning about electrochemical cells?
Yeah.
Yes. Yay. And Tyler's gonna hang out with us today. Yay. I hope you guys like Tyler.
This video isn't
Yeah.
Okay. So we are on page 61, I think. Yeah, 61. 6-1.
Introduction to Electrochemistry. So what's electrochemistry? Well, you might have guessed it has something to do with electricity and chemistry. And that's
Can you guys hear okay? Yeah? Okay.
exactly right. Specifically, electrochemistry is about the relationship between chemical reactions and electricity. When we're studying electrochemistry, there are basically two main ways that chemical reactions and electricity interact. Here's the first one. Certain chemical reactions can create electricity. Okay, so like that's what's going on in a battery. There are chemicals inside the battery, they react together making a chemical reaction, and that chemical reaction creates electricity. Okay,
Do you guys know how a battery works? Okay, so here's a battery. You've got a redox reaction. You've got some reactants in one area, and you have like the products in a different area. Okay? So you're really separating these two things so that you can have different things in different places. And when you have a redox reaction, one of the species is losing electrons, yes? And the other is gaining electrons. So if you can have, let's say, the species losing electrons here and the species gaining electrons here, what's going to happen to this end of the battery? Losing electrons, gaining electrons. It's going to get electrons, and that means its charge will be negative, and this end will be positive. And now you have a buildup of negative charge here, yes? And you have buildup of positive charge here. Is that like a happy state of affairs? No. So what you can do is you can connect this end of the battery and this end of the battery with a wire, and the electrons will be like, ooh, yucky, it's all negative down here, and they'll woo, to the positive end. Yes? And so they're moving from an area of high potential energy to an area of low potential energy. And that is how a battery works. And we're going to be looking at, yes?
What's like the acid?
Oh, the acid, that's going to be because you need something that, like, they're fairly complicated redox reactions. They're like with that one with permanganate that has like hydrogens in it. Yeah? So those hydrogens that you use to balance the reaction, they're necessary for the reaction to occur. So that's why some batteries have acid in them. If you get an alkaline battery, that's going to be one that works in basic solution. Okay, so it would have a reaction that involves OH minus ions. Yeah?
so that's the first way that these two things interact with each other. The second is that electricity can make certain chemical reactions happen that wouldn't happen otherwise. We'll look at examples of both of these situations. So if we're going to be talking about chemical reactions and electricity here, let's just take a minute to explain what these two things are so we can know what we're dealing with. First off, electricity. What is it? Well, in really simple terms, electricity is just movement of electrons. I got a bunch of electrons in this diagram. They're moving in this direction, so I have electricity. Often when we talk about electricity, we're talking about movement of electrons through something.
What do the electrons move through? Through the wire, absolutely, okay? And is this static electricity or is this current electricity? Current electricity. Static electricity is where the charges just sit there. Yes?
I have a question about the battery.
Yeah.
What if some battery like run out?
So you start with reactants.
Yeah.
And the reactants are like moving the electrons, and eventually you just run out of reactants. To be more specific, we actually come to an equilibrium. The system is very thermodynamically favored. So, right, like these electrons really want to get from here to here. But at some point, right? Like there's not as much potential energy anymore because they've already, most of the electrons have made it over here, so there's not as much pushing force, and that's why the batteries will die. And if you have a rechargeable battery, guess what you do? You plug it in and you make the electrons go the other way, right? So you move them back to where they were when the chemical reaction put them there in the first place. It's kind of cool.
So maybe it's through a wire, or through a light bulb, or through a battery, or something like that. But if you've got electrons moving, you've got electricity. So if electricity is about moving electrons, that means the chemical reactions that we're going to be talking about are also going to involve movement of electrons. And that means that these chemical reactions that we're going to be discussing will tend to be oxidation-reduction reactions, because these are chemical reactions where electrons move between atoms.
Okay, and just before we go on page 61, there is a misspent annotation because Tyler doesn't mention this. In current electricity, the movement is of charges. When we're talking about a wire, those charges are going to be electrons. Do we have electrons floating around in solutions? No. So when we're talking about solutions, which we will be, in an ionic solution or in a molten salt, what are the charged particles that can move? Ions. Okay? Yeah. Good stuff.
Okay, so here's how these two scenarios come into play. We can use electrons moving between atoms in an oxidation-reduction reaction to make electricity. The electrons are moving, so there's our electricity. And then for this situation, we can use electricity to force electrons to move between atoms to make oxidation-reduction reactions happen. Let's look at how that would work.
So what he's saying is that, if you have a situation where the electrons are moving from an area of high potential to low potential, that's going to happen spontaneously. But let's say you want to recharge your battery, you're going to be moving those electrons opposite of how they want to go. You're going to be making a thermodynamically unfavorable reaction take place by providing electricity to power that. Yes?
Can you recharge any battery?
No, they have to have a particular makeup, and I don't know all the specifics of it. I mean, in theory, yeah, but in practicality, I don't think it works. Yeah.
So here I've got an oxidation-reduction reaction where electrons are moving from A to B. How can I use this to create electricity along a wire? Well, what we could do is we could separate A and B, right? We know that electrons want to move from A to B, so if we separate them with a wire, then that means that the electrons moving between these atoms will have to travel through the wire, be moving through that wire, and bam, we've got electricity. Okay, now let's look at this example, okay?
Okay, so what kind of an agent would A be? Is A an oxidizing agent or a reducing agent? A is it losing electrons or gaining electrons? A is losing electrons, therefore it is being oxidized. Therefore, what kind of agent is it? A reducing agent. It is reducing B. B is the oxidizing agent, which is oxidizing A.
Let's imagine we have another oxidation-reduction reaction. Electrons transferring from C to D. But imagine this doesn't normally happen because C doesn't want to give up electrons and D doesn't want to gain them. Okay? Here's where we can use electricity. Okay?
Oh, and just before we go on to this part, there are some blanks up at the top of page 62. Electrons, I think the word is spontaneous, electrons want to move from A to B, yes? So what are we doing with A and B? We are separating them. So if we separate them with a wire, then the electrons moving between the atoms will have to travel through the wire. So want, separate, through.
We can take the electrical energy from a battery and use that to pull the electron from C here and to push them to D. Okay, so even if this reaction, the movement of electrons, doesn't normally happen, we can use electricity, we can use the electrical energy of this battery to pull and push the electrons to make this reaction happen.
Okay, now just before we go on, you guys are familiar with batteries and which is the positive terminal, which is the negative terminal, yes?
Yeah.
Okay, what's that terminal there? Positive. Does it make sense that it's pulling the electrons?
Yes.
Yes. And what terminal is this? Does it make sense that it's pushing the electrons? Yeah, okay.
Okay, so this is kind of a broad, big picture overview of electrochemistry. Now I want to show you two examples of these situations.
Okay, so C does not want to give up electrons or give away electrons, and D does not want to gain them or accept them. The electrical energy from a battery can be used to pull electrons from C and to push electrons towards D. And now we're going to get into all the different names for battery. There's so many, but none of them are battery.
One where we're using a chemical reaction to create electricity, and one where we're using electricity to make a chemical reaction happen. So here's how chemical reactions can create electricity. And to do this, to make electricity using chemical reactions, we often use a device called a galvanic or a voltaic cell.
Okay, what is the other name for a galvanic or voltaic cell? You're going to look on your piece of paper because it tells you. Electrochemical cell. Now, I will tell you that the word electrochemical cell is what regular chemistry 12 uses to mean a spontaneous cell. A lot of the rest of the world, AP included, uses galvanic or voltaic. All right? To further complicate matters, in some circles, electrochemical cell is used to refer to the whole broad category of electrical cells, both the spontaneous and the non-spontaneous. AP will not do that though. So for you guys, if it says electrochemical cell, you can assume that it is spontaneous. Okay, it's going to generate electricity. Okay, but just be aware that out there in the universe, I've seen it several places, electrochemical cell has been referring to both both galvanic cells, which are these ones that make electricity, and the other type, which are called electrolytic cells, which are the ones that require an input of energy. So don't get too wound up about it though, because that'll just be something you find in the world and you won't have to worry about it this year. Yes? I don't know. I don't know why BC chose to call it an electrochemical cell. I'd be happier if we just called it a galvanic cell. And why do we have another name? Why is it called a voltaic cell? I don't know. So many names, so many things. Okay, just know all three names, okay, for the spontaneous cell.
I've drawn one right here. The version that I've drawn uses zinc and copper metals. So let's take a look at the chemical reaction that's happening in this galvanic cell that is what's creating electricity. So here's a chemical reaction. We said that that galvanic cell used zinc and copper. So if you take a neutral zinc atom and put it near a copper 2+ ion,
what I want you to do is I want you to go look on your table and tell me what happens if you put a neutral zinc atom near a copper 2+ ion. And if you don't have a table, you can come and get one.
You can keep this one or?
You can keep it. You might want to hole punch it if you're going to keep it.
On your other phone number, I guess.
So what is going to happen if we put neutral zinc together with copper 2 plus? Neutral zinc together with copper 2 plus. Now there are 2 copper 2 pluses on your chart. Does it matter which one you choose as to decide whether this will react or not?
No.
No, it doesn't. If you had to decide which reaction would take place preferentially, which one would take place preferentially? The one with the higher potential or the one with the lower potential? The one with the higher potential. So the reaction we're going to get is Cu2 plus becoming copper solid rather than it just becoming copper 1 plus. Okay? And that is spontaneous. All right.
Electrons naturally move from the zinc atom to the copper. And so what happens there is the zinc takes on a 2 plus charge because it loses 2 electrons, and the copper becomes neutral because it gained 2 electrons. So why does this happen? Well, it happens because there's kind of a...
Okay, so let's just make sure we filled in our blanks. The galvanic or voltaic cell creates, what does it create? Electricity using a chemical reaction. If you take a zinc atom and put it near a copper ion, electrons naturally move from the Zn to the Cu2 plus. Not just Cu, but Cu2 plus. The zinc takes on a what charge? +2 charge, because it, what does it do with its 2 electrons? Loses 2 electrons, and the copper becomes neutral because it gains 2 electrons.
a tug of war between these atoms. Cu2 plus has a strong pull for electrons, and zinc, Zn, has a weaker pull for electrons. And that's why the electrons move. We can describe how they move in terms of oxidation and reduction. Zinc over here is losing electrons, so it is oxidized. Cu2 plus is gaining electrons, so it's reduced. Now, the most important thing about this process is that it happens on its own. All you got to do is put neutral zinc near copper 2 plus, and the electrons just naturally move. It happens on its own. This is a process that we can call spontaneous. It's spontaneous. It just happens on its own. Now, a really common question, that's a great question, is people say, okay, yeah, but like, how do you actually know that the electrons are going to move from zinc to copper? How do you know that copper has a stronger pull for electrons? Well, you can look it up. There is this chart that we'll be using a lot in electrochemistry that's called the standard reduction potentials. And it lists elements and compounds in terms of how strongly they want to pull electrons. So the higher you go up here, the more these elements want to pull electrons towards them.
So we have a standard what kind of potential? Reduction potential. And it tells us which chemicals have a stronger pull on the electrons, and therefore which species will pull electrons away from another. If you put zinc atoms near copper 2 plus, the electrons naturally move from the Zn to Cu2 plus.
We got copper 2 plus up here, and we got zinc down here. So the way this chart works is if copper is up here, if it's above zinc down here, then copper is going to be stealing electrons from zinc. Copper is going to have a stronger pull. So that's how we know that copper is normally going to be pulling electrons from zinc, and that this reaction is just going to happen on its own. So,
and how they came up with this table in the first place is basically, you know, they set up a whole bunch of these electrochemical cells, of these galvanic cells, of these voltaic cells, and they just measured the voltage, right? And saw which ones reacted with which ones and whether you get a positive voltage or a negative voltage. Okay.
This reaction, as we said, is what's going on in a galvanic cell. So let's see how we can use this galvanic cell to create electricity from this reaction. Okay? Well, we said that zinc is going to be giving electrons to Cu2+. But when these atoms just give electrons to each other just like that, it doesn't really create electricity that's very useful for us. But if we can separate the zinc and the copper 2+, then we can make the electrons travel through a wire in order for them to move.
So when we did that little poggle before the break, you remember how you had the little piece of metal and you put it in the solution, and sometimes it would react. Those would be spontaneous. Would we get any useful electricity out of that? No, because the electrons just go from the stick of metal and the little ions. Okay, so we got the stick of metal in the beaker, and then we got little ions floating around, and they'll come over here and they'll be like, oh, give me some electrons, and they'll grab the electrons. The electrons don't have to go anywhere to get to the ion, right? So that we can't get any useful work out of that. We have to force them to be separate, which is why instead of just one beaker, we have two beakers. We are separating the oxidation and the reduction so that the electrons have to move through a wire to get from the site of oxidation to the site of reduction.
And that is exactly what we do in this galvanic cell. Okay, check this out. We got zinc here in this container, and then we got a whole bunch of Cu2+ in this container. There's also Zn2+ here, but it's not really that important. So what happens is the electrons want to get from this zinc to this Cu2+, but in order to do that, they've got to go through this wire. So this is the path that the electrons take. They're moving through this wire to get from the Zn to the Cu2+, and check it out. They're moving along this wire, which means that they are creating electricity.
Where do they end up? Where do those little electrons end up? What do they do when they get to that beaker with the copper? Tell your partner, what do you think? What happens to the electrons when they make it to this beaker?
Copper ions, copper salt. But then once you use all the ions, it's copper salt.
What do you guys think? What happens? Where do those electrons end up? Yeah? Yes. Okay, so the electrons come over here and they say, oh, look, what a lovely positive charge that is. I'm negative. I would like to hang out with that positive charge. And so the copper grabs two electrons and it becomes copper solid. What do you think happens with that copper solid atom? It just ends up sticking to the rest of the copper. So what will happen to the mass? This is called an electrode, this piece of metal. What happens to the mass of that copper electrode as time goes on? It's going to increase. Now, where did the electrons come from in the first place? They came from the zinc. So if they came from the zinc, what's being left behind? Once the electrons have left, what's being left behind over in this beaker? Zn2+, and where would it go? Out into the water. So what's going to happen to the mass of this electrode? It's going to decrease. Yep.
Go into this piece of copper, and then they move here, wanting to get to the Cu2+. So we got electrons moving in this direction, and as I showed earlier, we can even take a light bulb or something and put it between here, and the light bulb will light up because there's electricity moving through this wire as the electrons naturally, spontaneously move from the zinc to the copper. All right? Now, in electrochemistry, we often want to describe what is happening in a device like this using oxidation and reduction. We want to be able to talk about the different parts of a galvanic or voltaic cell and say what's happening to them with electrons. So here are just a couple words that we'll need to know. These two pieces of metal, the zinc and the copper, are called electrodes.
Okay, so what are electrodes? They are the pieces of metal in a cell. Electrodes are almost always metal. They have to be something that can conduct electricity. And what kinds of elements are really good at conducting electricity? Metals. Can you think of a non-metal, a specific allotrope? What the heck is an allotrope? An allotrope is, anyone remember? Probably not. An allotrope is a specific version of an element. Okay, so like oxygen is O2, but ozone is O3. Those are two allotropes of oxygen. Can you think of an allotrope, a specific allotrope of a non-metal that conducts electricity?
I know. No, not necessarily. Just that no. No, not now.
Now, do you guys recognize what flavor of carbon this is? What allotrope of carbon this is? Which one is it? Graphite. Okay, so what I'm drawing here is a single sheet of the graphite. What's happening in between the layers of the graphite? Kind of. We have intermolecular forces in between the layers. What kinds of bonds are these? Those are covalent. Now, if you look at that and you think carbon, 1, 2, 3, 4. Oh, by the way, what kind of allotrope of carbon is this? This is diamond. How many bonds does each carbon have here?
3, 4.
What shape is it? What shape are each of these individual carbons? What molecular geometry? That is a tetrahedron, yes? Tetrahedral. What is the hybridization if it is tetrahedral? You're like, oh crap, I thought I never needed to know that again. Tetrahedral. Tetrahedral. We have 4 electron domains. Yes, what's an electron domain?
It's where they hang out.
It's where they hang out. It's where electrons hang out. Okay? And you can see them. 1, 2, 3, 4. Yes?
I'm listening.
Now, what are we hybridizing when we hybridize orbitals? We're hybridizing orbitals. Okay, so we're hybridizing orbitals. What kind of orbitals are we hybridizing? The this one and the this one. The this one and the this one. We're hybridizing S and P orbitals. Now, do you remember how to write a hybrid orbital? Okay. So let's look at carbon. Carbon, what is the electron configuration of carbon? One S, 2, 2S, 2, 2P, 2. Okay, now, if we were to draw that as like an orbital diagram, we would have the 1S. And what would we draw in there? Up and down. Okay, so that's 1S2. And then we have 2S, 2. And then we have 2P, 2. Where do I put the second one? Has to be an up in the next box. Now, what can we say about all the 2p orbitals? They all have the same amount of what? Energy. Therefore, we call them starts with a D. I like that. D. Degenerate. Woo. All right. Okay, so they are degenerate. Now, why do atoms bond? What are they trying to do? They're trying to fill their subshell. So according to this, what would carbon need? It would need 4 electrons, but how well would that work out for it? Right? Like it would take one of its electrons and share with somebody else, maybe a hydrogen or something, and another hydrogen. Now what's going on here? I've still got this empty one. Normally, when things bond, what do? You get one electron from each species, yes? So if we were to draw, say, methane, we would have carbon with its 1, 2, 3, 4 electrons, which we're drawing unpaired here. But in reality, are those 4 electrons all unpaired? Are those 4 electrons all unpaired? Those 4 valence electrons? No. So why are they unpaired here? Well, we're going to get to that. But, you know, we could have hydrogen here, and each hydrogen would share an electron with carbon. And then, oh, look, carbon has a full octet, which is great. Yes?
Yeah.
Because that is stable. All right. But this little Lewis model is not really jibing with the orbital diagram, which says I have 2 paired electrons and 2 unpaired electrons. What I really want is how many unpaired electrons? In order to make this structure, how many unpaired electrons do we want?
4.
We want 4 unpaired electrons. 1, 2, 3, 4. Yes? We want 4 unpaired electrons in order to bond. Yes? Yeah. Oh, the word promote. Yes, we need to promote some electrons. So what are we going to do? We're going to take this electron here, and instead of having it be paired up, we are going to promote it. So now instead of having what we had before, now what we have is we have 2s. I'm going to ignore the 1s because those are core electrons. They're not involved in bonding. We have the 2s. And then we have the 2p, which is lovely. But we still have a problem because if these are p orbitals, how do p orbitals orient themselves with respect to each other? How do p, x, y, and z orient themselves? As far away as possible. So we get one that goes up and down, one that goes side to side. Just here's fine. And then we have one that goes front to back. Yes? Okay, I'm sorry for the terrible drawing. But they are at 90 degrees to each other. Now, if we look at methane, is methane 90, are all the bond angles 90 degrees in methane? No. What are the bond angles in methane? What shape was it again? Tetrahedral. Okay, that's our little tripod. Come over here. There we go. What is the bond angle in a tetrahedral structure? 109.5. And quite frankly, AP is incredibly forgiving in terms of bond angles. If you were to say 110, they'd probably be good with that. So if you're like, I can remember 110 better than 109.5, you're probably okay. Yeah? 109.5 FM. Come on, I know. So we have these p orbitals that are at 90 degrees to one another, but we know that the hydrogens are not attached to orbitals that are at 90 degrees to each other. They are attached to orbitals which are at 109.5. 5 degrees to each other. So we cannot have p orbitals, because p orbitals are all at what degrees? 90 degrees. So after we have promoted this electron, what are we going to do? We're going to hybridize. So we're basically going to put them in the blender, all right? And we're going to end up with 4 orbitals that are all of the same energy, which means they are what? Degenerate. And so we have 1 electron in each of these. And how many s orbitals did we throw into that blender? 1. 1 s orbital went into the blender. How many p orbitals went into the blender? 3 of them. 1, 2, 3. Now, we started with 1 orbital and 3 orbitals. How many orbitals are we going to have in total? 4. And we have an S and a P and a 3. Now, do you have to go through this mental gymnastics every time you do this? No. What you have to remember is that this is the format in which we write hybridization. So it's going to be SP something. Okay, so your hybridization is either going to be SP, SP1, sorry, 4 choices. No. What am I doing? 3 choices. Oh my God. 3 choices. SP, which is SP1, SP2, and SP3. Yeah? And all you need to do to figure out which one it is look at the number of electron domains. How many electron domains are we using if we have sp3? 1 plus 3 equals 4. So there's 4 electron domains. Yes? 1 plus 2 equals 3. We have 3 electron domains. And we have 1 plus 1 is 2 electron domains. And electron domains can be a bond. It can be a single bond. It can be a double bond. A double bond is 1 electron domain. It can be a lone pair. Okay, so the electron domains can be a single bond. It can be a double bond. It can be a triple bond, or it can be a lone pair. We don't get quadruple bonds because it's very unstable to have that many electrons in the space between the 2 atoms. So, going back to graphite, I'll give you a second to finish with this, but going back to graphite, let's go take a look at graphite and figure out why graphite can actually conduct electricity. Oh, here it is. Now tell me what is wrong with this diagram at this point. What is missing? It's flat, but it is flat. Yeah? That's its 3D shape. It is flat. What is the shape around, what is the molecular geometry? What's the geometry here?
That is trigonometric.
Trigonal planar. And how many electron domains are there?
3.
3. And what's the bond angle? That one's easy.
This one is 101.
120. Okay, you take a circle, divide it in 3. Okay? But what's wrong with carbon at this point?
It's unhappy.
It's unhappy. Why is it unhappy? It's incomplete. So what's going to happen is you're going to have a double bond here, which will give, now this electron has 4 bonds and this electron has 4 bonds. How could I satisfy this one now? I could bond on the other side. Oh, look at that. Now I've got these guys who are all okay. What else could I do? Who's not okay yet? This guy here is not okay. What could I do to satisfy that one? Oh. What kind of bond have we added? What kind of bond have we added? A double bond. What's a double bond made of? A single bond is a something bond. It's a Greek letter. Sigma. Bond. Okay? It's caused by what kind of overlap? This kind of overlap or that kind of overlap? That kind of overlap, head-to-head overlap. Okay?
I know. We can't unlock it.
So that's a sigma bond. That's your single bond. A double bond is a sigma bond. Oh, plus 1 pi bond, which is side-to-side overlap. So what you guys are going to do for homework is you are going to finish watching the video and filling in up to page 68. Finish everything up to page 68. No, I'm reviewing for the AP exam.
That was a. Yeah.
Okay. Let me just press pause here and press print. Stop.